we've got a variety of different kinds of orbit. We've got that low Earth orbit, which is the cheap one. International Space Station, for example. International Space Station, for example, uses the low Earth orbit, uses the rotation of the Earth to give rockets a little bit of a head start in gaining enough speed to go into orbit for the centripetal force to equal the gravitational force. Got the polar orbit. Now, polar orbit has a time period of roughly, depends upon the actual satellite, roughly 90 minutes, which means that every time the satellite goes over the poles, goes around the Earth has rotated a little bit. And so it's used for global tracking or global observation. The type that is actually used quite a lot and is actually a much more expensive type of orbit is much further out. And we're going to explore this one in detail, okay? Because this is one that does come up a lot in exams. It's a lot further out. And it's going around the Earth. There we are. It's going around the Earth in the same direction as the Earth's rotation, above the equator, and its particular position is such that its time period is exactly 24 hours. So I'm going to leave a little gap before I name it. So in other words, if it's above the equator, so it's kind of going around matching above the equator, I do apologize. It's above the equator. So it's going round, but it's matching the rotation of the Earth. So imagine you're stood, say here. That satellite would be above the equator, but would always be in the same position in the sky at any time of day. So that is basically, it's synchronized with the rotation of the Earth. So we call it geosynchronous. Another word we use for it sometimes is geostationary. So it's always pointing in the same direction. So that's what we use for things like satellite TV. If you think about it, if you've got satellite television, you've got a dish on top of your house, and that dish always points at the satellite. So because the satellite's in geosynchronous orbit, that dish always points in one particular direction. If your TV satellite was in a low Earth orbit, your satellite dish would actually have to turn and track the satellites as they go overhead, which would be very expensive to set up. So those are three particular types of orbit: geosynchronous or geostationary, polar orbit, and low Earth orbit. In an exam, you would probably get asked a question about the features, or maybe suggesting a particular type of orbit for a particular type of satellite. You've just got to think about what it's used for. If it's a satellite where it's got to be launched as cheaply as possible, or it's got to be serviced as frequently, so you have to get people and supplies up to it, then you'd use a low Earth orbit. Or if you're launching many satellites, you'd launch a low Earth orbit. So, for example, the big GPS alternative constellation of satellites that's being launched at the moment, they're all in low Earth orbit. Polar orbits is if you want to have one particular satellite tracking the entire planet. So that would be a polar orbit. So what you'd use that for is if you were sending a space probe to go into orbit around Mars. You can't send lots of space probes to go around and orbit Mars because that'd be very, very expensive. So what you do is you would send one satellite and it would go into a polar orbit or something similar to it. And the third one is geosynchronous or geostationary. Okay, I'm just going to respell geosynchronous because I've not spelt that correctly. It's my dyslexia, unfortunately, is a problem. Alexa, Spell geosynchronous.
Geosynchronous is spelled Geosynchronous.
And that is the correct spelling of geosynchronous orbit. Okay, so that would be used in any situation where you want one satellite and you want one receiver to track that particular satellite and make use of its signals. So that's the basics of orbits. As I said, in exam questions, you are asked two basic questions about the type of orbit. One is to be able to identify the name of the type of orbit. It might well be to identify its features, or you'll get a question about the use of a particular satellite. The one you get in detail quite often, the two you get in detail are low Earth orbit and geostationary orbits. The geostationary orbit one's very, very common because it's one that's used quite a lot in the real world. So what I'm going to do is I'm going to show you a worked example, okay? So a geosynchronous orbit just uses some of the physics that you've already learnt about. Whoops. Geosynchronous orbit. Okay, be very careful about the spelling of that. Things you need to know about it. Well, you need to know, for example, that its time period is 24 hours. Okay. Now that's the bit that you're asked usually to recall. It's 24 hours and it's above the equator. What you might get is you might want to work out the radius of orbit. It's a very common exam question. So to get the radius of its orbit, you're using some basic physics, using the idea that I showed you last week, where I mentioned the idea that centripetal force is equal to the gravitational force. Okay, so bear with me. Is that someone knocking? No, it isn't. So we're using centripetal force, so that's going to be m omega squared r, okay, is equal to the gravitational force, which is big G, the universal gravitational constant, mass of the Earth times the mass of the satellite over r squared, okay? Now, I should add that the centripetal force can also be given by mv squared over r, but this one we're not going to use because we don't know v. We can work out the angular velocity though. It's fairly simple. We know that the angular velocity is 2 pi over the period of rotation, okay, which we know is 24 hours. So we know that if that period of rotation is 24 hours, we know that's going to be 24 times the number of seconds in an hour, which is 60 minutes in an hour and 60 seconds in a minute, or you can memorize the number of 3,600, which is 60 squared, but it's probably easier to try and work it out from first principles. And that gives me 8.64 times 10 to the power of 4 seconds, or 86,400 seconds. So that gives you a period of rotation. So we know that. So all we've then got to do is do a little bit of substitution and a little bit of tidying up. So we know that if that's the case, we know that m omega squared r, the centripetal force, is big G, big M, little m over r squared. So we know the mass. Omega squared, well, omega is 2 pi, so it's 2 squared is 4, pi squared is pi squared. multiplied
Excuse me,
by...
Gary.
Sorry, yes?
W is equals to 2 pi over t. What formula is that?
That one, it comes from the idea. Did you do the units on Seneca on circular motion?
Yes.
Right. So you know that that is the angular
Angular
velocity.
velocity. Okay.
Yeah. If you think
Yeah.
about it, the angular velocity is the angle subtended in radians
Over the time taken.
over the time taken. So to go around in one circle is the angle of 2 pi radians. That's the same thing as 360 degrees. And the time
Okay.
taken to go around in one circle, well, that's the orbital period. That's the time taken. So that's where
Okay.
that comes from. Does that make sense?
Yes, it does.
Okay.
So
Thank you
these
very much, Ralph. Thank you very much.
can we use mv square over r is equals to the gravitational force to do what you're doing?
Not really, no, because we don't know what V is.
Okay.
In some questions, you might get asked to calculate V, in which case you'd need to use that. But in this case, I don't think that's particularly useful at the moment because we want to know the radius of the orbit.
Right.
But that's a good question. Thank you for asking those questions. It's really important to do so. So we can see straight away from this that the masses cancel. The mass of the satellite cancels. So a lot of people think that heavier satellites have to go faster or slower or something like that. It's not true. For a given radius of orbit, the thing that actually affects it, bear with me, the thing that affects the actual radius of orbit is the time period and the mass of the thing that's actually going around. So that's the mass of the Earth. So if we want to work out the radius, we end up with, if we rearrange it, we get r cubed, because that goes up there, is equal to the gravitational constant times the mass of the Earth. Now r squared's gone up there, so we're going to multiply both sides by t squared, and we've got to divide both sides by 4 pi squared. Now, as we've got that, that's the cube root. So to get the radius, we need to do the cube root. Now, the cube root is a function on your calculator, but there are a couple of ways of doing it. Just in case you get stuck, what you're looking for in your calculator is one that's like an X with a cube and a 3 above it. Okay. The other way to do it, if you don't have that function on calculator or you can't find it, if you've got X to the power of Y button, and you just say that Y is 1 over 3. That's another way to do it. If you can't find the cube root button on your calculator or your calculator doesn't have one. So here we are. So let's just substitute in our numbers. So we know G, well, that's on the formula sheet in the exam. So I happen to know that's 6.67 times 10 to the power of minus 11. We're multiplying it by the mass of the Earth. Well, in an exam question, you'd be given that. So that'd be 6 times 10 to the power of 24. And then we multiply it by time period squared. So it's 8.64 times 10 to the power of 4. You have to square it. Divided by 4 times pi squared. And we want to find the cube root of all of that. In real terms, when you're doing an exam, what I advise you to do is to work out what that is first, write down the number, and then do the cube root of it. It just seems to be more reliable. Little tip: most commonly made mistake on this type of question in an exam is forgetting to square the time period. For some reason, it seems to be a bit of a sticking point. So you calculate that all and you end up with some weirdly huge number of 4228918 or something like that. Well, obviously that's a completely unrealistic level of precision. We're not going to work this out to the nearest meter. So we'd say 4.2 times 10 to the power of 7 meters. So that sounds about right. Okay. So is that realistic? Well, that is realistic, isn't it? We're looking at several thousand kilometers above the surface of the Earth. The Earth is a few thousand kilometers wide in radius, so we know that that's going to be that's going to be sort of a lot more than that. Okay, does that make sense so far?
Yes.
Okay, so that's one of the way. That's one of the particular ways of, you know, with types of question you might get. You sometimes might be asked to calculate the speed, in which case you would use mv squared over r equals m omega squared r. Okay, and you can work it out that way if you know the radius, or you can equate mv squared over r to big G big M little m over r squared. And if you you know, if you want to do it that way, okay, depends on the question you've got. I always say that one of the best things to do is to highlight what you're given. As your second half of the lesson, I'm going to ask you to have a go at some exam style questions, so you have a chance to do that. So that's one particular type of question that you'll get. So the next bit I want to show you goes beyond the orbits and really goes to what's called escape velocity. Now, if you think about it, when you see a rocket being launched from Earth, if it's a space probe, what we want it to do is to escape Earth's gravity. But the gravitational field stretches over an infinite distance. So how do we do that? Well, what you do with escape velocity, it's the basic idea is the kinetic energy of the space probe or the rocket becomes the gravitational potential energy. Okay, remember that is the energy, sorry, delta GPE. Remember that is the energy required to take the object from infinity that, by the way, is a symbol for infinity, to a point, a distance r from a body. So if you think about it, if you put that much energy into an object in terms of its kinetic energy, that kinetic energy will become zero once the body's reached infinity, which sounds a little bit odd, but it does work. So the idea is meant to be that if we take the kinetic energy of an object, we say it's equal. Well, you know that with gravitational potential energy, it's a negative number because it's an integral. But it's an integral of the force with respect to r.
Gary.
Sorry?
Gary.
Yep.
Excuse me. How I don't understand how the energy is required to take the objects from infinity to a point. Isn't it like from a point to infinity rather?
Absolutely right. I'm so glad you asked me that, because I've realised I've skipped a little step. Remember you did that Seneca bit on gravitational potential?
Mm-hmm.
Yeah. When you did it as gravitational potential, that was the definition, but there's a particular reason why.
Wow.
The reason why, if we think about it, if you want to do work on an object, if you want to take it to infinity,
Yes.
the work on the object is going to be the force times the distance. Yeah?
Yes.
Okay. So if you want to work out if it's force times distance, okay. So it's F. Now, have you done integration in maths yet?
Yes.
Right, now, okay. So if we want to work out the force times distance, here we've got to think about it. It's basically, it's the integral of the force times the distance going from infinity to the point of distance r from the object. Now we know the force is going to be it's the integral. We know the force is big G times the mass of the object times the mass of the planet over r squared. And this would be dr, wouldn't it? Because r is just a
Mhm.
distance. So if we take it from infinity to r, we know that we've got big G, big M, little m. Now the integral is going to be r, isn't it?
Yes.
And it's going to be minus because it's -2. That makes sense?
Yes.
Okay. Going from
Isn't it
infinity
going
to
to be
r.
r cube over? Isn't it going to be r cube over
If you think about
r,
it, if you've got the integral of x squared is equal to,
x cube over 3?
yeah, it goes up, yeah?
Yeah.
X cubed over 3, yeah? That makes sense?
Yes.
Okay. So the integral, so if you've got x to the -2, that would actually be x to the -1 because that's gone up times
Yes.
-1.
Yes.
Yeah?
Oh, yes.
Okay. I mean, you don't really need to know the derivation for physics, but I think it kind of it applies it because it is a confusing idea about going from infinity to the point of distance r. So if we're thinking about it, we think very carefully. We've got the distance r, so we've got G big M little m over r, okay, negative, minus big G big M little m over infinity. Well, if you think about it, if you've got any number divided by 0, that means it can be divided an infinite number of times. So we know that any number divided by infinity must therefore also be 0. That makes sense? So
Yes.
this expression here is equal to 0. So we end up with minus big G, big M over R. It's a minus because remember the power has gone up by 1, which so it's gone from -2 to minus it's gone from -2 to -1, and then divided by the same number.
Yes.
Okay, so that actually then comes out. So that then is the gravitational potential energy. You can tell it's a Friday. I'm making lots of spelling, lots of writing mistakes, but that is correct. And that was a formula that they kind of just showed you on Seneca Learn. But you've shown a higher level of understanding by actually wondering where that comes from. So I'm really impressed that you came up with that. So thank you very much for that, Owen.
You're welcome. But doesn't that mean in the definition, Gary?
Oh, the
Like,
definition.
the
Well, if you,
definition, isn't it like isn't gravitational potential energy like moving an object from a point on the earth far away from to a point far away from the earth, right?
right. Well, this is why it's a negative number.
Yeah, I understand there's a negative number, but in the definition,
Yeah.
it says from a point from infinity to a point. I'm
Yeah.
wondering, isn't it from a point on the earth to infinity to like if to like somewhere else? Don't you get what I'm saying?
No, it's a good question. So let's have a think. That's where the reason why is that's where the negative number comes from. And when you come to look at electrical fields which follow the same pattern of rules, you'll actually we'll come back to this. But if you think about it, if it's going from infinity to a point R, you're not putting energy in, are you? You're getting energy out. So if you're
Okay.
getting energy out, then that's going to be a negative amount of energy because you're putting negative energy in. It's a bit like
Okay,
if you've got a bank.
Gary, what's the definition of infinity?
Infinity. Well, that's a huge branch of mathematics that's slightly beyond me, but even a degree level physicist. But basically, the number infinity
Yeah.
is it's basically the biggest number possible and then some. It's a very weird number. There's some really weird bits of philosophy that actually come from that number infinity. But the way I always think of it, imagine you've got a basket with X apples in it. Okay.
Yeah.
If you've got, say, a basket with 4 apples and you're sharing it between 2 friends, how many apples do they get each?
2.
2. Okay, that's because once you've given each friend 2 apples each, that's 4 apples gone.
Yes.
Now, if you've got 1 friend, then that is basically divided by 1. So you can only divide it the number of apples times, if that makes sense. Now, if you've got 0 friends, you give each friend an apple out of that basket of 4. How many apples have you got left?
None.
Have you?
None.
Think about it. You've got 4 apples, okay?
Yeah.
But you've got no friends to share them with.
Oh, no friends.
Yeah? So you're going to give all your apples to your no friends. So
Oh,
if you've given an apple to each of your no friends, and Pascal's just joined us at a very interesting moment. I think you might need to watch the first part of this to understand what we're talking about. Owen and I are actually getting into some fairly heavy philosophical debate here. I don't mean that in a patronising way. That's actually quite an interesting question. If you've got 4 apples and you give an apple each to 0 friends, how many apples have you got left?
4.
4. So how many times can you keep giving an apple to your 0 friends? How many times could you do that?
So many times?
Yeah, an infinite number of times. It never stops.
All right.
Yeah, does that make sense? That is about as good a definition of infinity as I can come up with. I always think of it, the bit of it that's useful to me as a physicist is knowing that any number divided by 0 is infinity, and any number divided by infinity is 0. That's the useful bit. So that gives you, anyway, that formula for gravitational potential energy. We know it's negative because its definition is the energy required to take the object from infinity to that point of distance r. We know that in real terms, we're not actually putting energy in, we're getting energy out. So it's a bit like that bank account, isn't it? You've got 0 in the bank account. If you take the energy out, you've effectively put in a negative number of money. So that's why it's got the 0 there. Thank you very much for that question. I really appreciated that. It's a good mental exercise for me of a Friday morning as well. Now, here we are. So escape velocity. What we're going to do is the idea behind escape velocity is it has enough kinetic energy to overcome that changing gravitational potential energy, okay, to take it to infinity. So as that GP is the energy required to take it from infinity to that point, we know that we can say that's going to be equal to big G, big M, little m over r, okay? So if we want to try and work that out, well, if we want to try and sort of neaten that up a little bit, first thing that happens straight away again is the mass of the object you're actually accelerating up to that escape velocity is irrelevant. It doesn't matter what it is, whether it's a football, a person, a rocket, or a building. It's the same velocity. It's going to be the same velocity. So all we then do is a simple rearrangement. It's, well, v squared equals 2 big G, big M over r. So the escape velocity is 2 times the universal gravitational constant, which is on a formula sheet. For the Earth, it would be the mass of the Earth, divided by the radius of the Earth. If we're taking it from the surface, that would be the radius of the Earth, and square rooted. And it's that simple. That is the key formula to do that. It's not on your formula sheet, but it's a fairly easy one to work out. And in fact, when in an A-level exam, if an examiner is asking you about escape velocity, you're usually expected to do that particular sort of derivation. So, I mean, you can work out the escape velocity of the Earth. It's a very common exam question, so you'll probably come across it at some point in your practice. So rather than do that, I'm going to do a worked example on this one for you. And this is the last part of the main part I'm teaching here. So this is going to be a worked example. I'll show you how you do it. This was an exercise I did with a physics teacher about 5 years ago. We were at a staff meeting and things were going rather slowly, shall we say. So the two of us decided to do a little bit of a physics task, because both of us were physics teachers. And at the time, there was a space probe which had actually travelled to a comet. So we did a little bit of a task using data from that particular comet. So here we're going to present you with a science fiction problem. Imagine you're an astronaut. An astronaut is the same thing as a cosmonaut, same thing as a taikonaut, just depends on which country they're from. An astronaut's American, taikonaut's Chinese, and a cosmonaut is Russian. Bear with me. I'm just going to refocus my camera. It's gone a bit off, I think. There we are. So let's imagine the astronaut has been sent to the comet, but he's been stranded. Something's gone wrong with his spaceship. Okay, so an astronaut is stranded. On a comet, and we said, imagine if someone was there, knowing the idea that anything that's launched into space, if it's traveling at escape velocity, it won't come back. So an astronaut is stranded on a comet. Could they escape by running? If you've got a comet, comets are much smaller than planets, and comets are much smaller than planets, and therefore the gravitational field is much weaker. So the escape velocity will be much lower. Because if you look at the formula for it, the escape velocity is 2 times big G, which is actually a very tiny number, times the mass of the comet divided by the radius. Well, the mass of a comet is much less than the mass of a planet, and so the escape velocity would be less. And that was our sort of theory. That was our sort of weird question. And then we sat down with our notebooks looking like we were copiously making notes, but this is what we're actually doing. We did a few estimations. We looked at what values we would need. So we know, for example, that kinetic energy of the astronauts would have to be equal to the gravitational potential energy from the surface of the comet. Okay, we know the ends would cancel. We know that's therefore half v squared equals G big M over R. So we could then work out the escape velocity. That's going to be the same as we had before. I'm kind of shortcutting it a little bit here. 2G M over R square rooted. So we could think about it. We could actually work it out, because we would know, for example, that G is a standard number. It's the same everywhere in the universe as far as we know. 6.67 times 10 to the minus 11. Now the units are meters cubed per kilogram per second squared. Okay. Want to know the radius of the comet? Well, the comet that was in the news at the time had a radius of about 1 kilometer, which is 10 to the power of 3 meters. Okay, so that's roughly the size of a comet. It's an average size for well, it's a little bit large, but it was the comet that they'd sent this particular space probe to. So you could work out the mass. Now we worked out the mass because we knew the density. We knew roughly what the density of a comet was, and you assume the comet to be a sphere, to be perfectly round, and you could work it out as the area of a sphere, 4/3 pi r cubed. So you work out the volume, multiplied by density, and you get the mass. But I'm just going to give you the mass. The mass by our calculations was probably about 4.2 times 10 to the power of 12 kilograms. Okay, so still quite a high mass. But then all you do is you work out the speed. So the velocity, the escape velocity would be 2 times 6.67 times 10 to the power of minus 11 multiplied by 4.2 times 10 to the power of 12 divided by the radius, which is 10 to the power of 3, all square rooted. And true to form, I've always said that you need to sort of do your calculations carefully. I always said you should calculate the bit that's inside here first, just because it makes it less prone to mistakes. When I did it, we worked it out to be about 0.56 square rooted, which is about 0.75 meters per second. Okay. Now, for those of you who want to know what it is in sort of real money, that's about 1.7 miles per hour, or about 2.7 kilometers per hour. You can work that out. You can calculate it. It's trivial. But the point is that, could you run at that speed? Well, I can certainly run at that speed. Whether or not I could do it in a big space suit is debatable. But our conclusion was that an astronaut, if they were exploring the surface of a comet, they basically wouldn't need any kind of lander. They could actually just set foot on the surface of the comet and then start running when they want to get back to their little sort of orbiting spaceship. But you can see that you can do that particular type of exercise pretty easily. The idea behind the escape velocity is escape velocity is the velocity for which an object has sufficient kinetic energy to overcome its gravitational potential energy at the surface. Now, the next bit to show you, last bit I promise, because I know I've been talking at you for quite some time and I'm probably going to get cut off if I'm not careful. So what I'm going to do is, I'm just going to show you one more thing, and that is the change in gravitational potential energy. It's something that comes up again and again. Often when you're given when you're given a situation, when you're given an exercise, you've got the planet Earth, you've got sort of a rocket on the planet Earth. There it is. And you're given sort of a height. The mistake that people often talk about, the height, the energy required to change that height there. Okay. Now, the two mistakes people make is they use mgh. Can't use that because g is not constant. For a big change in height, it's not going to be constant. For picking up a book from the floor to the desk, g isn't going to change. But for taking a rocket from the surface of the Earth to a geosynchronous orbit, that radius is going to change, so g is going to decrease as you go up. A lot of people just do this. They say GP is equal to big G, big M over H. Well, that's not correct either. That doesn't work. What you do to get the change in gravitational potential energy is you look at the two gravitational potential energies. You look at the difference between the gravitational potential energy at the radius r. Oops. So that's going to be big G times big M, little m over r, minus big G, big M, little m over. Now this time the radius is going to be r plus delta H. Okay? That makes sense?
Sorry?
Does that make sense?
Why do you have to subtract?
Because it's the difference between the two. You're looking at the gravitational potential energy here and the gravitational potential energy here.
Isn't it over r squared?
No, because it's the energy, remember. So we said before in our earlier part, I'm just trying to find the paper that I used to describe it. Yeah. For those of you who are into your calculus, you know that work done is force times distance, okay? But actually, it's work done is force, is the integral of force and multiplied by distance for a change for a change in r, okay? So if that's the case, then what you've got here is you've got an integration. We know that the force is big G, big M, little m over r squared. But if you integrate that, you end up with minus G big M little m over R. That makes sense?
Yes.
Okay. And that then, when you actually sort of when you do a full sort of integration, you end up with that gravitational potential energy, and that's also why it's a negative number, because to go from infinity to a point of distance r from the center of mass of a planet, you're getting energy out. You're not putting energy in, but its definition is the energy required to take it from infinity to that point. So it's a negative number. Okay, again, I must say, I'm really glad you asked that, because it is a common mistake. So the common mistakes that people make are confusing gravitational potential energy with gravitational potential without the energy. It's not the same thing. That's for an object that is per unit mass. Okay, in other words, little m is equal to 1. So if we think about it, the gravitational potential energy, which is minus big G, big M, little m over R squared, doesn't matter which one uses big G, big M and little m, but if we think about it, if that's per unit mass, that's the energy required per unit mass, oops, not R squared, it's R per mass, we end up with minus G, big M over R, okay? Now, the common mistake, and it's one I just made there because I wasn't concentrating properly, because there's lots going on around me. Remember, energy is proportional to 1 over R. Force is proportional to 1 over R squared. Okay? That makes sense?
Yes.
Okay? That is a common mistake in exams. Okay? That's the way it is. So a lot of people write GPE is equal to 1 over is equal to over R, all this lot over R squared, which I just did because I wasn't concentrating. So that's how easy it is to make that mistake. Even I make it if I'm not thinking. Let's get rid of that. Don't like that. There we are. Got rid of that. There you go. Pretend it never happened. Yeah, it's a common mistake. A lot of people make that mistake, and it's one of the two mistakes that people make with these questions. Now, I'm going to give you a little task to do. I've put it on show my homework, but I'm going to
Gary,
give you
one last question.
Yeah, sure.
So the force is the gravitational potential?
No. No. Remember, you've got 4 basic formulae. Starts with Newton's law of gravitation. Okay? Yep. You know that it's okay, so that's the force of attraction between 2 bodies separated by a distance of r. Yes. Make sense?
Yeah.
In a derivation from that is the force per unit mass, in other words, the gravitational field strength, is the force per unit mass. So that m is 1. Okay. The next one that we did earlier on in the week was you learnt the gravitational potential energy. That's taking it from infinity to a point of distance r over r squared, and the potential, which you don't get very often, but it does come up, is simply is the potential energy per unit mass. I've done it again. I'm not concentrating. Must be Friday. There we are. Okay, it's not over r squared. Remember that, not over r squared. So the gravitational potential is gm over r, okay, because it's per unit mass. So these are energy. These are force. Okay, does that make sense? Does that make sense?
Yes.
Okay, right. So your tasks, I'm going to give you 2 tasks. The main task Right, so have a go at those attached questions. Okay, have a go at those attached questions over the weekend and for the rest of this lesson. A little extension task. And I'm going to go back to my initial page that we looked at before. Now, I have said something here. I've said its height of orbit is 2 times 10 to the power 6. And task 2, very simple. Is to work out, should this be the height or the radius? Okay. Now that's an extension task because you'll need to go off and do a little bit of research for that. Okay. So it doesn't matter that are written up here. You've just got to know the approximate orders of magnitude, really, more than anything else. But I want you to sort of maybe push yourselves a little bit and work out whether that is actually the height of a low Earth orbit satellite. That's its height above the surface of the Earth, or is that the radius? And the reason for that is because that's another common mistake that people make. They take the height to be the same thing as the radius. It's not quite right. So you need to find that out, okay? Is that all okay?
Yes.
Okay, any questions?
Nope.
Okay, everybody. Well, in that case, I will let you. Hang on. In that case, I'll let you get on with it with that task. I look forward to seeing a submission in the next few days. Take care, everybody, and I'll speak to you again on Wednesday, I think.